Victor Lawrence is an engineering icon. He was behind the first ever instance of telecommunication between the United States and Europe, then with Asia, and eventually with Africa. In the 1970s, when data transmission speeds were limited to 300 bits per second, he revolutionized digital filter design, a technique now integral to most digital signal processing chips. This technique, which is used to suppress oscillations and stabilize both fixed and adaptive digital filters, is now implemented in most chips on the market today. Furthermore, Lawrence played a pivotal role in enhancing global accessibility by architecting and leading the development of AT&T's first 2400 bit per second full duplex modem. This modem he would eventually introduce to Africa, being the first in history to do so on the continent.
Throughout his career, he has held various influential positions, including leadership roles in data communication research at Bell Labs, as well as lecturing and research positions at Stevens Institute of Technology. Most recently, Lawrence was awarded the National Medal of Technology and Innovation granted by the President of the United States. He is also a National Inventors Hall of Fame inductee, an Emmy Award winner, and a Fellow of AT&T Bell Labs.
Unfortunately, due to some camera storage issues, our recording was cut short around the 30-minute time mark. We wish we could provide you with the full-length version, but sadly we cannot recover the footage. We will try to include extra images throughout to fill in some of the lost information that we missed, and we appreciate your understanding.
Hello, my name is Zidanni.
And I'm Emilio.
And your world.
We hope you enjoy our conversation.
So I am Victor Lawrence. I started my career in Bell Laboratories. And in there, I started as a member of technical staff and rose through the ranks to be the vice president for all of advanced communications technology. And in there, I had about 500 or so scientists and engineers,
wow,
PhDs working there with me in the lab. Now, I began working in the area of digital signal processing. What happened was that when I was a student in England, my professor gave me the chance to be able to work in the lab and do some testing for the transistor. The transistor was invented in 1949. And this was in 1968, thereabouts, that I got the chance to work on the transistor. It took about 20 years to from this invention to commercialization. Technologies take that much of time in the industry. Mm. Now, what it was that the head of Bell Laboratories, the president of Bell Laboratories, around the 1949 or before then, gave a challenge to some of the engineers. They were physicists, chemists, and material scientists and engineers. He wanted to replace the vacuum tube. I don't know whether you folks know about vacuum tubes, but vacuum tubes were things that were used originally in the network and in the TVs and so forth and radios. But vacuum tubes were very inefficient. They were very hot as well. Mm-hmm. And so he gave the challenge that can we do something in solid state? And he gave the challenge to 6 people, one a physicist, a chemist, a material scientist, and engineers. They were a combination of these. And they came up with the transistor. And so that was the birth of the transistor. But the thing which is important, it was multidiscipline. The people that were doing that were not just one discipline of engineers or whatever. They were physicists, they were chemists, they were material scientists, and electronics engineers.
So the transistor was born in Bell Labs?
The transistor was born in Bell Labs in 1949.
And it was a combination of not just engineers, but so many different backgrounds. That's amazing.
That is right.
Yeah.
And so you would find that if you really want to do something very significant, you may have to look at it as a multidisciplinary effort, because just one discipline may not be efficient and sufficient to do this.
Wow. Yeah, that's something that Bell Labs has really interested me when I first started researching. The laboratory is like, yeah, you have people from so many different studies, backgrounds. So I guess my question for you would be like, what's the biggest challenge, or what's the thing that really surprised you when you started working, at Bell Labs, and you have to collaborate with a bunch of different type of people?
Well, yes, and I will tell you also about my own history and my successes and failures, and so you can deduce the surprise from there. So I was recruited in 1974 from England, and they brought me straight to Bell Labs. But one of the things they said was, okay, you've done your thesis, and in your thesis you are learning how to you designed for us digital filters, going from, before then the network was all analog, and you had analog filters. And analog filters at that time consisted of capacitors, inductors, and resistors. That's how the analog filters were constructed. And then, so in the digital filter domain, the digital filter, instead of an analog signal, it's a digitized signal, zeros or ones. And so what we use for that is a multiplier, an adder, and some delay elements. Those are the building blocks of a digital filter. So they told me that, okay, you've done a lot of simulations, computer simulations. Now, can you build a digital filter for us? And so the very first thing to do is that the simulations are sometimes in floating point arithmetic and very long number of bits. But if you have to build it and then put it into a network, you have to use a finite number of bits. So it could either be 8 bits, 16 bits, but not more than that, because the bigger it is, the more costly it is. So I started building this filter. And I was building it in the two's complement arithmetic, because the things are ones or zeros, you have to have multipliers and adders to have a digital filter. So I started building with that. And my filter became an oscillator. And mainly because of two things. Mainly because of the quantization. When you have a two's complement arithmetic, for instance, you have to quantize it to a fixed number of bits. Now, believe it or not, it's very tricky. Two's complement rounding or two's complement truncation result in different characteristics and different signals. Because when you multiply two signals together, you have to quantize it so that it fits the 8 bits. And sometimes you have to ensure that there's no overflow, because you add some things together, two signals together, and if they are bigger than your 8 bits, then you have overflow. And that overflow leads to oscillations and so forth. And the same thing is the small quantization also leads to this. So that was my first failure.
So you're really restricted by the technology of your time.
The technology of the time. And then I also did not understand two's complement arithmetic very well.
I guess for the for each of us and also the audience who's watching this, can you please briefly explain what two's complement and quantizing is?
Oh, any number of bits, any signal can be put into a number of bits. There will be the sign and then the number of bits associated with that. And so you could have the type of arithmetic could either be a two's complement arithmetic, or it could be a sign and magnitude type of arithmetic. So this is why I went to a mathematician to work with a mathematician to say, look, can we really try and understand this two's complement arithmetic? At least the rounding and the truncation of it and its effect. So I teamed up with a mathematician in order to understand this. And we came back, we understood exactly what to do. Sometimes when you round, sometimes you have to truncate. You see, rounding and truncation is like, say, if you have this if you have, say, 2.4, if you truncate it, it's 2. If you round it, it's also 2. It's only when you have 2.6 that you round it, it becomes 3. But then if you truncate 2.6, it's 2. So you have these arithmetic things going through the filter, and that leads to a combination of oscillations.
Yeah.
So you really have to understand when you truncate and when you round. And doing that, and that's where the mathematician helped me to do that. And so I then was able to build the filter, and it worked very well. But you know what I learned out of that was I learned how to build the best oscillator or a touch tone. Oscillators are used for touch tones. You know, this cell phone, you have the numbers, and each number really represent 2 tones. You see, because when you you punch something on this, it goes to the network, the central offices or networks, and there it then finds out what number you are calling, and then it will then route it to the destination for you. Now, each number represented by 2 tones.
Two what?
Each number is represented by 2 tones.
Okay, 2
0
tones of
to 9.
oscillations. Okay.
Yes.
Okay.
Yeah. And the tones are oscillators. Yes. In fact, if you go to the bank and you go to the ATM machine, you can see, you punch it and you hear tones.
Yeah, I do, yes.
Yeah, in ATM machines. I mean, this one doesn't give you the tones, but the tones are there. But in ATM machines, once you press them, they are tones.
Oh, so the tones actually have a corresponding meaning. Oh,
the tones give you the numbers.
okay.
The number 9 has got 2 different tones from the number 7.
Wow, I never knew that. Wow, that's actually...
But if you think about it, when you're... Yeah, no, I never thought about that either. I'm on the same boat as you, but when you think about it, yeah, you're dialing a phone and it makes different noises every time. Wow, that's something I never thought of.
And you hear different noises. Those noises are too. And so I learned how to do it for AT&T, how to generate the cheapest, the simplest, more stable way of doing tone detection and tone generation.
So I just have a question. Why do the offices, why do they differentiate between numbers using tones and oscillations?
Well, the central office, because you have the number, your number, I think is, one of you has got this number 347 at the beginning. Yours,
yes,
is it?
Yes. 347.
Okay, and then there are the other the other 7 digits. So everything is 10 digits. So the 347 tells you that, okay, there are people who have 347 numbers. So they go to you folks. And then, of course, the other 7 digits. It brings it exactly close to you, so that it comes to only your phone. That is how the network works.
Okay.
Yeah. It based upon these tones. Now, one other thing too as well is that if your speech that you have, if you look at it and you record it on an oscilloscope or something, it's a waveform. But to do it digitally, you have to sample it. So you sample it and you quantize the level of the analog signal. And that's what you use through the network.
Okay.
So you sample and then quantize it. Now you have to quantize it because the analog sample is infinite precision. But you can't put all this infinite precision through the digital network.
And your work at AT&T is to find the most efficient way to differentiate between these oscillations.
Yeah, well, yes, that's one. Now, in the filtering itself, the filtering also allows you to take different signals, your speech, somebody's speech, and multiplex them all together and put it through the network. And therefore, you have to filter. That's where the filtering comes in. So I was known to be a very good person knowing how to do filtering best. And when you start looking at doing filtering, then they asked me, so what about modems? And in a modem, a digital modem is nothing more than filters and modulators. Okay, so I became since I knew how to do the filtering, I became an expert in this area. And so they asked me to build some of the digital modems. And I built, in fact, in this cell phone, there's a modem inside it. Because all it does is takes all the characters you have. The characters are 26 characters. You take those characters, and each character is put in an ASCII form. Okay, and so those are the things. So you transmit that. So when I'm transmitting either your speech or your data, in fact, your data that comes, it is data that I'm transmitting in ASCII form. Your A, B, C, each of them is represented by so many bits, maybe 8 bits, 16 bits, whatever it is. But it's ASCII characters. If you start learning about the numbers and characters, the 27 characters we have now are all in ASCII form. In fact, you look at this now, whatever your name is, my name L has got so many ASCII characters.
Yeah, we begun to learn about that actually in our classes a little bit. There's certain problems where you have to sort a word or sort something in alphabetical order, and you have to compare ASCII values. So,
that's right.
Yeah.
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 So I became an expert in modems. And with the modems, was transmitting data from your computer or from your cell phone. What you transmit is data, all bits. Because you take your characters, you put them in ASCII characters, and then you transmit them. Okay. So I did the first a lot of high-speed, full duplex simultaneously. That means that on the same telephone line, both you're transmitting and receiving on the same one line. So I did the first full duplex modems over the international networks.
Wow.
So, but I was able to do that because some of my classmates, whom I did my PhD thesis and things, were in the United Kingdom at the British Telecom Labs, and I came to the US to the AT&T Labs. So I had colleagues there, and so we could then work together and transmit and prove the feasibility of a full duplex.
So was the first transmission using the duplex between the U.S. at AT&T and them in the
British
UK?
Telecom in UK.
Wow.
Where my classmates are.
Yeah, that's crazy.
Some of them, Mike Buckley and others, but they are my classmates. Because we were sitting in the same lab, and whilst we were working and doing our PhDs.
Another crazy or really interesting thing that I read about you and about data transmission is when you first started back in 1970s.
Yes.
It was just 300 bits you were limited to.
That's right.
Just 300 bits, and now we're in the gigabits. We're in the gigabits by
That's
far
right.
now.
Yes.
By far. So
when I did my 2400 bits, 4800 bits, 9600 bits, people were so happy and this about now you are gigabits. So they did in a span of 1970s, 80s, so a span of 40 years now you are talking about gigabits per second.
Yeah.
So let me just continue a little bit and then you can listen. So what happened also was that they said, okay, so you know how to transmit data very well over the international network. And in this case, it was Atlantic, over the Atlantic. Of course, we also had to work and do it also over the Pacific before it was standardized. The techniques we had was standardized so that everybody can build it. So then they asked me this question. They said, since you've done this, can you have secure voice over the network? So then it was very simple. Okay, what should you do? I told you that you have your analog signals, analog voice, you digitize it, you sample it, and then you digitize it. And so there are bits. And then you put that through the network. At the other end, you take the bits, and then you have to put it through a digital to analog converter. But when you have bits, you can scramble it. You see, scrambling, that is encrypting it. In fact, when you are doing a lot of cyber security and things, all you are doing is encrypting. You have your things and you randomize it, so that, for instance, if I have all the bits, I can take these bits and randomize it in a way that you are the only one that can know how. I will tell you how I randomized it, and so you are the only one that can be able to unscramble it. I'll scramble it in such a way. Scrambling is very simple. You take the bits and you do exclusive OR with another key. That's what they normally tell you. You have a key in encryption here.
Yes.
So the key is used to scramble the signal. And it's only when you have the key that you will be able to decode the speech.
Yeah.
And so it was in this way. So they said this. So we built the first secure voice terminal. And all it was is that we have them from the microphone. You digitize your speech. You scramble it with a key. Use a modem to transmit it. At the other end, the modem gets the signal, it unscrambles it, and then puts it out as this. So that was a secure voice terminal. And we built this, and we happened to do this in the 1980s or so, 88, 89. And it was used by the President of the United States talking to his generals and so forth. So we call them the STU terminals, secure telephone units.
And that's still how modern encryption is today, right?
Yes.
Yeah, that's still how
It's still how encryption
that's still how
is
we
done
encrypt
today.
it today. And
Yes.
you were a part of one of the first group of people, it seems, to.
Yeah.
start
And
working.
then they said, okay, you've done data, you've done speech, voice. What about video? And at that time, your TV was analog. And so if you want to do something digital as well, you have to take the video, also sample it. But video is a little complicated. You have red, green, blue, the various colors. Yeah, so you treat all the various colors, these things separately. You digitize them. And then you use a modem. So your TV in your house today, since it's digital, all it is the video signal digitized, compressed, and then used in a modem to transmit it. Yeah, so that's what. So they said, okay. So I did video as well. And then the interesting thing that they said was, oh, you are an expert in trying to transmit data and things over the Atlantic and over the Pacific and things. But no one has been able to transmit this to Africa. So they said, okay, that's where I started working on it, and it became a ring around the continent of Africa, and we called it Africa One, a ring, because in order to be able to, if you want to go from, you look at this continent, there are 38 countries on the coast. So if you want to go from America to any of those countries, you shouldn't go have a line from each one. It is best if you have a ring, and then you get to one of the countries, and then you put a ring around the continent, and then you put your signals along the submarine ring.
A ring of telephone wires?
Yes, submarine cable. A submarine cable is nothing more than a fiber cable.
So rather than map it down the coast straight down, you have it almost
a ring. Right. And so once you are on the ring, you can go from one country to the other on the ring. So we put a ring around it, and then we called it Africa One. And so that's how so from the US, we went to Europe, and from Europe, we go to Morocco and those places.
Does Africa One still exist today?
Oh, it exists in different forms because there have been improvements. And in fact, today, Facebook, Meta, has got one that they call To Africa. It's based upon what Africa One is, but they call it To Africa. It's much more powerful, many more fiber, many more strands of fiber, and much faster. That's how this thing is. So, and then the submarine cable is under the ocean, and it's about 5 miles from the top of the ocean around to the seabed. It's about 5 miles, 7 kilometers, 5 miles. And so the cable is at the seabed of the ocean. And when you get to a country, you bring it up. You see, you tap it and bring that part up. But the rest still continues going through other countries.
So it's all running underwater, like
all
sort
running
of wrapping
underwater.
around the continent.
Yeah, all running around the continent.
That's so interesting. Wow.
So those are some of the things. Now I can tell you what I'm doing now, but we can ask some questions before the future.
Sure, yeah. So, I mean, one of my biggest questions, I think this was easy to hear. As you were talking, I could almost kept reminding me of my question is that you seem to have like almost you could look into the future and tell what's going to stick around. Like, you know, your work in data communication still exists, is still very important today. Encryption still very important today. So it seems like you're a visionary in some sense. So I guess it's only natural to ask you, like, what do you think, you know, now happening in technology and engineering? What's exciting to you, and what's really interesting?
But you know, with me, you know, I think it's been assured as some people see things as they are, and they ask why. Others dream of things that are not, and they say why not. So that is the philosophy in research. You will see this, you say why, okay, but you should dream of things that are not, and then you would, and then that would help you focus and look into the future. So the question you asked was?
Yeah, the question I'm asking is, right now, what's really exciting to you in engineering?
Well, I can tell you. Well, you know, today many people are talking about two new technologies. You know, we talked about the digital world, but it's mainly using classical physics. But people are now thinking about the next step after classical physics is quantum mechanics. Instead of classical mechanics, it's quantum mechanics. And that is going on now. People have not been able to build a complete quantum computer yet. We know how to build classical computers, and you've been using them in the lab and everything. So I think the future looks at it as quantum mechanics. And in Stevens here, there is Professor Yuping Kwan. He is the expert on quantum physics here. And they
He has a startup, Quantum Computing Inc. Right?
Yes.
Down in Hoboken.
Yes.
Oh, really?
Yeah, he does. Yeah.
Yeah, he. So instead of classical physics, you are doing quantum.
Yeah.
Yeah, quantum mechanics.
Quantum physics is
Yes.
and quantum computing
Yes, and-
is really interesting to me too. I think if you were to ask me the question I just asked you, I might have answered the same.
The same way.
And
And then the other one is artificial intelligence. So artificial intelligence is another strike of technology that is coming up. I think you all use it. You use ChatGPT, you use other things and so forth, all AI. And I think you find that there was going to be even, I believe that there will be a new, instead of a BS in computer science, a BS in this, you may have a BS in artificial intelligence, data science. There's BS in data science and other things, yes.